I welcome all the participants to the first session of the second day of our 4 days program, workshop on modeling and simulation of physical system organized by Department of Textile Technology, NIT Jalandhar. Now, Professor Bhaj will deliver the lecture on the topic modeling physical system using bond graph, some examples from 5:30 p.m. to 6:20 p.m. And in second session, the topic casualty in physical system from 6:40 to 7:30 p.m. So Professor Bhaj, please.
Thank you, Professor Bhowmick. So, good evening to everybody. The topic today is modeling physical systems using bond graph, and we'll be doing some examples. But since we decided yesterday that we will have a mixture of causality and examples together, so I thought it will be okay if we bring in the topic of causality, which we had scheduled a little later, and if we mix it along with the session today. So the presentation has been planned accordingly. First of all, let us proceed with, so this is not just causality of sources, but also the constitutive equations as well as causality. We'll be covering both together. First of all, let us come to the source of effort, as we discussed yesterday, and I think much discussion is not necessary on this, but all the same, the source of effort, it is represented by the notation SE, and it provides power to the subsystem to which it is connected, and because it is a source, it imposes the effort. It's an effort source, so it imposes effort, as is intuitively understandable, and that is actually its output. The output when seen from the end of the source, it is the output of the source, and that is imposed on the subsystem. So this becomes an input to the subsystem, and we know that the other variable is flow, and naturally flow should be input to the source. It is the output from the subsystem, but it is input to the source. So the question arises, if the flow which the source receives, if it changes, will it result in a change in the output of the source? Will that happen? Ideally, it is not supposed to happen. The moment we say it is a source, ideal source, we mean that it will impose an effort no matter what is the flow which it receives. Whatever is the flow which is input to it, it doesn't matter. It's somewhat like gravity. Within reasonable limits, near the surface of the earth, we know that depending upon the mass of the body, the force of gravity is going to act on it. It is going to be imposed on the mass. Okay? No matter how much of flow is applied on the source, on the source of gravity, but the force of gravity is going to be imposed on it. Okay? So this is the idea of source of effort. In electrical systems also we have sources, and within reasonable limits, we can say that they are sources of effort. Say for example, our 230 volts AC which we come across quite frequently. Within reasonable limits of load, we, we understand that the source, the point, the connection point, it provides us 230 volts. If there is a significant um, if there is a significant load connected to it, if rather if you connect it, if you connect a short circuit to it, I mean you just short the terminals, then what happens is that there is a possibility that depending upon its internals of the source, the potential may drop. But that is a weakness, that is the non-ideal nature of the source as it happens in this case, and we know that we take care of this by providing suitable fuse. Okay. So, but in the ideal case, when we are talking of ideal sources, the source is supposed to provide a given voltage. It may be an AC, it may be a DC, okay, it doesn't matter. It is supposed to impose the effort. If it is a source of effort, it is supposed to impose the effort on the subsystem to which it is connected. No matter what is the flow that it receives, no matter whatever is the input to it. So this is the characteristic, this is the constitutive equation or the constitutive relationship for a source. This is its constitution. Okay. So we have seen this. So naturally it's clear that the stroke, causal stroke which we discussed yesterday should be placed here. Next, let us see the source of flow. In a source of flow, we have, as the name suggests, the flow is to be imposed on the subsystem to which it is connected, no matter whatever is the input which the source receives. So the output of the source, which is the effect of the source, is not affected by input to it. Okay. I hope this point is clear to you. So where should the causal stroke be placed? It should be placed near the source of flow. And you can see that it's just a matter of a stroke. Causality can be written unambiguously, okay, on the picture itself. Now let us come to junctions. Yesterday we saw the one junction, we also saw the zero junction. Today let's see what about the causality of these junctions and also the rules regarding the governance of these junctions or the constitutive rules for these junctions. Okay. We discussed yesterday that the one junction is a one. You can connect any number of bonds to it. All the bonds will have the same flow. It's a common flow junction. Okay. So they will all have, I am putting bonds, power bonds to this one junction, and all of them have the same flow in them. Now the question is, suppose we talk of causality. I have shown causal strokes like this. Okay, only one bond bringing in the information of flow into this one junction. Okay. Suppose in this one junction we have a number of bonds, number of power bonds connected to it. It doesn't matter which one, I'm just taking the same as the one which we had taken earlier. And just to represent that it is a common flow junction, I am representing it by a suffix here, F. So F is the same flow in all these bonds. I hope all of you can see it. Now suppose in this one junction, if a flow is to be maintained, or if it is to be respected, that suppose two bonds bring in the information of flow. If two bonds bring in the information of flow, what would happen to the one junction? Would it be able to maintain its relationship? It's possible that the two flows that are brought into the one junction may be different. In that case, the one junction would be in a dilemma, which flow to accept. Okay? So as far as the one junction is concerned, the rule is, or its constitution is, that only one bond can bring in the information of flow. All the other bonds must respect it. Otherwise, it cannot actually maintain its constitution. Okay, I hope it's clear to you. So this is the grammar for the one junction. It's as simple as that. So in this case, what we had done is that we had brought in flow into this junction. Okay, so we bring in flow into this junction, and the process of bringing in flow is represented by just putting a causal stroke here, because automatically the other end receives flow. This becomes the effort receiving end. So the other bonds necessarily must come in a causal pattern like this. It may be any one of them, any one bond which may bring, but only one bond can bring in the information of flow in a one junction. Naturally, only then it will be possible for the one junction to maintain its characteristic of maintaining in all the bonds the same flow. Okay? So you can see that the flow in all these bonds is the same, but efforts are different. Efforts are all different, and let's see this. We have got here E1, E2, E3 and E4. The one junction as such, it is a power conserving junction. It does not create power or destroy power. In fact, it's just like an exchange. Whatever comes into it, it just goes out. Okay? It doesn't retain anything with itself. So in that sense, whatever power is brought into it, let's say that in this case power is brought in through bond 1, the same power has to be distributed in the other bonds. So P2 plus P3 plus P4, you can see this. In this constitutive, in this example, this is what seems to be happening. Now if we are to write power in terms of efforts and flow, we know that it is a one junction, all the flows are the same. So we will write it as effort 1 into flow. This is equal to effort 2 into flow plus effort 3 into flow plus effort 4 into flow. So what does it mean? We can cancel flow from both sides, and so it yields just a summation of effort